Okay, so good morning, everybody. Welcome back to these lectures. I see that I've lost quite some of you, so I could somehow guess it from the questions I found in the box. So I found quite many questions, and I've decided to spend the first part of this lecture just answering these questions. Some of them are very relevant. And, but let me start first by pointing out at this question that I found in the box. So I don't know if the author of this is in the audience today. If he is, please do put in this box something like, yes, you're allowed, meaning that I'm allowed to use that drawing in my website. So that drawing is essentially, later on you can come here and have a look. But it's essentially a compass that doesn't work at all. You know, so that when I found it in the box, I was very frustrated. I thought, oh, I completely, you know, failed my duty, because it's a compass, very messy compass, a lot of strange faces. The nicest thing that there is a POVM, which is somehow like a bomb, so it really seems like POVM, and I really liked it. So I realized from that question that, you know, you're at least some of you are quite either skeptical or confused about the whole story. And which is also confirmed by some of the questions I found, other questions I found in the box. So let me start just going through the questions and see if we can get a clearer picture about what I'm going to speak, what I speak about. Perché faccio sempre questa cosa. I'm a disaster with topology. I've never been able. Okay. Okay, first question. I put questions in order. The first question was about the postulates. It was someone complaining about the sketchy way I introduced the postulates. I don't want to justify myself, but obviously when you introduce the postulate, you actually never know whether people consider that you are doing something completely useless, because physicists should know the postulates, or whether you should be more precise, simply because the way of introducing postulates may vary from one person to another, from one course to another. In particular, what I read here is, for instance, it's not clear what this means. So the way you formulate the first postulate is the following. To every system, and the reason why I'm not saying quantum system is simply because systems are quantum. It does not, now I'm being very personal, in the sense that this is my viewpoint. Not only mine, but so systems are quantum, and some systems which are quantum may behave as if they were classical, meaning according to classical laws, just because of some conditions being verified. Okay, so systems, to every single physical system, it is associated a Hilbert space. Okay? Each density operator, meaning positive operator with trace equal to 1, is a legitimate state of your system, meaning that it contains all the information that you need in order to reconstruct the distribution of measurement results upon that system. Now, clearly enough, writing this on the blackboard is a little bit boring. That is what that arrow means. So a system, a Hilbert space, density operators. Density operators are called states. Okay? Is that clear? Now, I mean, seriously, if it's not clear, ask me now. I don't want to have problems with this. Pardon? Please.
So how is this correspondence, if you delineated sort of portrayed into the formal correspondence on the wall? So how does this arrow, so you talked about the physical system, and there's an underlying Hamiltonian, and then the state is raw.
Not Hamiltonian. There's no Hamiltonian whatsoever. That is a Hilbert space.
A Hilbert space, okay. So could you then dress into, dress this picture with your words, like sort of in this sentence?
So you are disturbed by this arrow, essentially.
Yes, and the semantics is very different now, though.
Okay. Yeah, let's say that the arrow follows from the fact that the Hilbert space is usually called the state space. Okay, so it's the space of the states or state space. And that is why, but I mean the arrow you can avoid it. Okay. Okay. Now, second question. Okay, second postulate simply, I mean, I think you don't need that much explanation about it. However, let me say it again. The second postulate states that now, let me say a few words about this postulate now. This is not equivalent at all with the Schrödinger equation, time-dependent Schrödinger equation. The reason being that in order to go from this postulate to the Schrödinger equation, you need to assume conditions upon the nature of time. You need to assume homogeneity of time, and meaning that everything should depend on differences between different points along the time arrow. And you also need to assume composition of time, meaning that whatever happens from T0 to T2 can be split into T0, T1, T1, T2. Okay? Time, not operations. I mean, that is, I don't want to enter into this. I mean, this really goes into foundational of quantum mechanics, which is not the topic of this course. But the reason why this is important is that, in fact, this is at the heart of the way of how we realize quantum processes. What this object says is that it is enough to have a unitary here and here to describe the change of a state of a system. It doesn't matter whether this change occurs in time or not. Okay? So time is just a parameter. It's not the Schrödinger equation. There is no Hamiltonian involved in all what I've said yesterday. When you have to construct a device, when you have to design a device, and then you need to realize this unitary, then you will need a Hamiltonian. But at this level, no Hamiltonians. Please.
If I take, for example, T plus delta T, and I construct UT and UT dagger or something like in order to construct the infinitesimal evolution. Is it possible formally to define an Hamiltonian which describe UT?
Yes.
Okay.
Yes. So you can actually, in quantum computation, you usually have these two possibilities. Either you have the Hamiltonian and you ask yourself, how much time should this interaction last in order to obtain a specific Q? So for instance, if your unitary is a spin flip or bit flip, so it's something that reverses the spin of your system, then you can decide, I have this interaction, so I know the Hamiltonian, I construct U of t, and I say if I let this interaction work for time equal pi over 2, for instance, in some dimensionless quantity, it will act as a spin flip gate. Or you can do the other way around. You know you have to obtain a spin flip gate, and then you look for the Hamiltonian such that if you let it work for a certain time, it will have that effect. Is this the correct answer? Okay. Please. Yes. Yeah. Until the fourth, there is just one system. So whatever happens is due to something internal to the system. So for instance, you don't have time-dependent Hamiltonian in this scheme. Okay? Because if you have a time-dependent Hamiltonian, it means that there is something else that induces the dependence on the Hamiltonian. Okay? I see you lost. I mean, this is... Okay, I go on. I didn't think I had to discuss about the postulate. Okay, mathematically speaking, what are those objects? M. And here someone wrote M belongs to H. No. M belongs to real numbers. So what is M? Whenever you have this M in your notes from the course of yesterday, M is one of the possible results of your measurement. So it's a real number. Okay? While the operator, do you remember the third postulate, for instance, in the POVM or POVM version, is you have a set of results. We will give example today about this because otherwise you don't understand. So you have a set of results. These are the results of your experiments. So they are either real number or something that you can associate with real number. It can be a color, for instance. In the example I will give later, it will be a color. Red, blue, white is the color of your detector. You have a detector and it lights up in white if it detects something. Okay? So these are the results. And what the measurement, as in the postulate, does, it associates to each of these results an operator. So what this means is that to each result you associate an operator. And the only thing which is required is that these operators are positive and they sum to unity, to identity, sorry. Then you obtain your postulate, which is the probability of getting this result, given that you are observing a certain property, capital M, or if you prefer, making a certain measurement, on a system which is on the state rho, equals this object. So these are bounded operator acting on H. So yes, this belongs to the space of the bounded operator acting on your original Hilbert space. And the same holds for the operator M, which is nothing but those via which you can write this in this form. And these are called measurement operators. Okay, and M, capital M without hat and without anything, is just the type of measurement you are performing, which is the same as saying is the property that you are measuring. Is that clear? Yeah? Good. How does the definition of rho change for infinite dimensional Hilbert spaces where the trace may not be well defined? Well, that is not true. So the trace is always defined on separable Hilbert space. There's no problem. It may be not finite, but the trace is always well defined on separable Hilbert spaces. Separable Hilbert spaces, I remind you, are Hilbert spaces whose dimension can be infinite, but where, such that it exists at least one orthonormal basis having the cardinality of the natural numbers, meaning that you can count the element of the basis. Example, harmonic oscillator, okay? You can use the Fock representation, and you have a basis which is 0, 1, 2, 3, and you count them. It doesn't matter. It goes to infinity. The dimension of the Hilbert space is infinity, but still is countable. And that is what a separable Hilbert space is. If you want, you can use a continuous orthonormal basis, like position. But that doesn't change the nature of the Hilbert space. Okay? It's important not to be confused about this. Okay? Mathematicians, it depends on the school where they come from, include separability in the definition itself of Hilbert spaces. Most mathematicians say that if a Hilbert space is not separable, it's not actually a Hilbert space. And they introduce this idea of rigged Hilbert space. But I don't want to enter this. Okay? So you can always find a countable orthonormal basis, and that is not related at all with the fact that the Hilbert space is infinite dimensional or not. If we get to the trace, as I said, the trace of any operator can be infinite, but if the operator is a density operator, by definition, the trace must be 1, so no problem. Okay? Okay, 4. Oh, this is nice. I'm not able to imagine an example of measurements which are not projective for closed systems. Now, this is interesting in the sense that measurement, by definition, is an operation that opens your system to the external world. By definition, measurement is the most important situation where your quantum system has to speak with the measurement apparatus. So by definition, measurement cannot be a problem of closed system. It must be a problem of open quantum system. And actually, that is the reason why we study them in open quantum systems. Having said that, I will give you now some example of P of M. Okay, this is just to copy this. So, first of all, we concentrate upon a qubit because it's simpler. Okay, so we take a qubit. A qubit, as I said yesterday, is a system whose Hilbert space has dimension equal to 2. And we choose on the qubit what is called the computational basis, usually indicated with the cats in this way, computational basis. This can be whatever. What physically implements this can be whatever. A spin, an atomic system, an ion trap, and blah, blah, and blah, blah. Now, in measurements, you need your system. So this is your system. And again, you see this way of associating the system with the Hilbert space. So you have your system, which means that you have a Hilbert space and an orthonormal basis. And then you need to have a measurement apparatus. Now, really take the viewpoint of an experimentalist and say you have a measurement apparatus that, I had to write it down because otherwise I would have not remembered, that measure in the computational basis with probability P. What does it mean? It means that it can, with probability P, do nothing. It can, with probability 1 minus P, detect whether your qubit is up or down, is 0 or 1. Okay? You see the point? This means that, and this is typical in all these kind of generalizations, you actually have in your brain the idea that there is some disturbance. So your measurement apparatus is not perfect. Or in any case, there is a possibility that it simply does not detect anything. And you have to include it in the description of your problem. So how do you describe this problem? Well, these are your operators. You have, and you see M here is black, which is, with probability P, it doesn't detect anything. It doesn't work, okay? And this is a classical probability. This has nothing to do with the results of your measurement. This is something which is in your measurement apparatus. Then you have now, these are the measurement operators. These are the elements of your measurements as they appear in the postulate. Okay? You can easily check that if you sum them, they equal to the identity. So they are okay. And you can easily check that they are positive. And so what you do, you go, for instance, and ask yourself, okay, what is the probability for this apparatus to turn red if, for instance, the state of my system is 0? No, sorry. I need bigger glasses. Is Q, where Q is any combination . Now I'm using the cats, but just because it's easier. Okay. Okay. So you ask yourself, so this is my apparatus, my measurements, okay? And I ask myself, what is the probability that my apparatus turns red if my state, the state upon which I want to perform the measurement, is Q? You make the calculation. This, because through the postulates, is Q, 0, 0, times 1 minus P. 1 minus P obviously goes out of the trace, and so you have 1 minus P. Okay? Do you mind if I give you another example? Now, the reason why I want to give you another example is that it is very often found in books that P of EM are used in order to discriminate states better than PVM. And the example I'm going to give is very interesting from this viewpoint. Are you happy with this example? Did you understand the difference with the projective measurement? It's a very simple example. I mean, it can sound slightly trivial, but it's just to show you the formalism. Yeah? Okay. Second example. You take this apparatus. And notice that the reason why this way of introducing the apparatus is typical. So when you say you take this apparatus, it means you write the operators of the POVM. Okay, so you take this apparatus. Again, you work with a qubit. And now this is what you define. Okay, so again, you can check, exercise, that these are legitimate measurement operators, elements of the POVM. You can check that they are not projectors, although they might look as projectors because of the presence of this last one. They are positive and okay. Now, this kind of measurement allows you to discriminate, to do something that projective measurement will never allow you to do. Discriminate between a state 0, 0 and a state plus plus. 0, 0, I mean this, and plus plus, I mean this. Okay. Why is that? Because if you evaluate, let me just evaluate this probability. You trust me. If you don't, you do your calculations as an exercise. This is usually defined plus. Okay. So what does it mean? What does this mean? It means that if you make your measurement and you never find your system, that your apparatus turning red, you're sure that your system is in the state plus. Obviously, in the quantum sense, so you need to repeat your measurement. You need to construct a probability. So you repeat your measurement, and you see that the measurement, the apparatus never turns red. You're sure then your state is plus. If it never turns blue, your state is 0. Sorry, the other way around. If it never turns blue, your state is plus. If it never turns red, your state is 0. Please.
These probabilities are defined on an ensemble average of all repeated measurements. This is
well,
the line.
That is, yes, that is the postulate. And there's no other way out. So,
I agree. It should be clear that some
yeah. So whenever you write P, is the difference with the usual way you deal with the measurement is that there's no expectation value of operators here. Because when you have an operator, the usual, just let me say this, perhaps it will clarify. When you study in usual textbook and you have a Hermitian operator and you define the expectation value, what is that Hermitian operator? It is nothing but the sum of all the measurement operators, each weighted by an eigenvalue, by what you call eigenvalue. Okay. Now, if you put everything together, you see that using this postulate, then you obtain the usual version of the expectation value.
But you're saying that here you explicitly do not invoke Hermitian operators?
Not at all, yeah. And that is the reason why you don't even say, when in this framework, in these books, I mean in Nielsen, but everywhere, you very rarely find written something like, you measure the Z component of. What you usually find, or the X component, or the energy, or whatever, what you usually find is you measure and then the operators. You perform the P of EM equal, and then you have the operators. So the measurement is specified by the measurement operators. And that is crucial because that is how detectors work. When you detect something, you simply have this kind of picture.
But this detect something must still be an eigenvalue of something going click. It's like a number operator, right? 0 or 1. Something click.
Is not an eigenvalue of the operator. It's just one of these M. Now, okay, didn't want to go into this. So the connection is this one. You have your results, which are not the eigenvalues. How do you build your operator? You sum, and here you have what is called the calibration function. This is the eigenvalue. But you need to have a calibration function. And then you have your operator. However you want to write it. It can be a projector. If you write it as a projector, then you have the spectral decomposition of your operator. Key point is that this is your eigenvalue, and this is your result. They are not exactly the same thing. You need to calibrate your apparatus in order to find this function.
I agree.
Okay.
But it's physical then. This calibration is translated.
It's really something, when you weight yourself, you jump on a scale and you have a needle that moves, and what you read is an angle, is not your weight. And then you have a calibration that tells you that that angle corresponds to 10 kilos, 20 kilos, or whatever.
Why then are these, okay, again, why are you so explicit on not invoking or not giving so much emphasis on the calibration? Like, okay, what do you want to retain the generality apart from the calibration? Let's say, what do we gain from this abstraction?
The possibility of describing situations that you otherwise cannot describe.
Give us an example like that.
I mean, even this one I give. There's no Hermitian operator associated to this measurement because this is not projective. This is not the measurement of some quantity. This is state typically, P of EM are used for state discrimination. And state discrimination is not the measurement of a property. State discrimination is really saying, what is the state of my system?
Okay, we'll discuss it later.
Okay. I hope you're happy with what I'm doing. I'm obviously cutting part of what I wanted to say during the course, but I think that it's important to clarify these things if some of you are, as I see, is interested in this. I hope the others don't mind. Ok. Dove sono le altre? Le ho perse. Eccole. Come? Alla discussione. Ma alcune di queste servono, quelle di oggi le lascio alla discussione, ma queste servono per oggi. Come faccio? Okay, so what Andrea was suggesting is that I can leave some of this question to the discussion tomorrow. So I will do it for those which are not necessary for today. Okay, so these were necessary. I wanted to clarify. Then there are three more about Markovianity, marginal, and the Naimark Theorem. And yes, in this probably Andrea is correct. Is perhaps not necessary to go through these ones now, and we will speak about them tomorrow during the discussion. Okay? So I can go on. Okay, so where did we stop yesterday? As we are speaking about measurement, let me still go on through the Naimark Theorem, which is actually one of the questions which is there, and it is interesting for what we will see today. Perhaps this also helps understanding the difference between the P of EM and the measurement you are used to. So the Naimark Theorem, sometimes spelled like this, says that any P of EM is a PVM on an enlarged Hilbert space. Okay. And it also demonstrates that the relation is the following. The P of EM operator has this form. The enlarged Hilbert space, let me call it like this. So let's say that this is on a Hilbert space H, and this is the enlarged one where A stands for ancilla, sorry. Okay, so let me call the main system gamma. I need this index. where this is the state, the initial state of the ancillary system. It looks obscure, but essentially what the theorem tells you is the following. As I said, the P of M is nothing but a quantum process. So you enter with your system, then you have your P of M, and you come out with the state of your system conditioned to the result obtained M. The theorem tells you that this scheme is completely equivalent to the following. So what does it mean? It means that if you want to represent a P of M, what you can do, you can think about it as a process where your system, the systems that you observe, interacts with an ancillary system that you prepare in a precise state. Let's call it 0. This is, you prepare it there. Let me write it with the, for consistency, like this. Okay. And then you let the two systems interact, and then you read the ancilla. You perform a projective measurement on the ancilla, not on your system. Now, why is this interesting? This is a typical scheme of measurements that you do, for instance, in quantum technologies. Think of this. You have the qubit, your interesting system, this one, which is, say, an atomic system. And you have it inside a cavity where an electromagnetic field is present. And you want to know whether your system is in excited, let's say that you are only interested in two levels, in two states of your atomic system. So I want to know, is it up or is it down? Is it in the first excited or is it in the ground state? So what you do, you actually let a photon go into the cavity, interact with your atomic system, and obviously, depending on whether the atomic system is in the ground state or in the first state, it will absorb or not your photon. Then the photon goes away, and you measure, for instance, this is a typical example done in a laboratory in Finland. You measure the increase of the temperature in a resistor due to the fact that the possibly emitted photon, when entering an electronic circuit, producing electrons, causes in the transistor. Did you understand? So you have your two-level system, you have a photon. If the two-level system is in the up state, the photon, goes away. It doesn't interact at all with your system. So it goes away, it goes into some electronics, photoelectric effect, electrons, increase of temperature in a resistor. My system, if I see increasing temperature, my system was up. The state of my system was up. I let it go, the system was in the ground state. The photon is absorbed, nothing happens. There's no increase in temperature whatsoever. My system was in the 0 state. State discrimination. So this is a typical P of M situation. Okay. You cannot actually think about it in terms of Hermitian operators and measuring properties. It's something different, but it's a typical measurement process in quantum technologies, and it's relevant. Okay? So that's why the Naimark theorem is so important. Tell me, please. Yes.
Is that, like, we just measure the temperature of the series?
Yeah.
But
is not the system. And actually, when you measure the temperature, you are already in the classical realm. So the final measurement is actually a classical measurement. What is produced before is, so in fact here, with respect to the example I gave you, you actually have access to this M later, not directly, because you need the photon. You would, but okay, never mind. You understand. Other questions? Okay. So this structure here is not much different from the one we saw yesterday for the general quantum process. So let me get back to that expression. Ah, in effetti posso usare quelle di sopra. Ok, never mind. So what we have seen yesterday, okay, another question that was around that I want to clarify. Someone asked, is a quantum process the same as a quantum operation? Oh. Ah, yes. Okay, so let me just say this thing and then we interrupt and then we start again. The thing I wanted to say, quantum process and quantum operation is not the same thing. Quantum process is the process and quantum operation is the formalism used to describe the process. Okay, so quantum operation, for instance, is a set of operators, are the Krauss operators. The process is phase damping, decoherence, or things like that, that we will see in the second part of today. Okay, so we will see precise examples. But they are two different things. Okay, so back in 10 minutes, Andrea. Yes. Now, someone yesterday asked me to make you notice that in order to obtain this result, we have used this property, which follows from the fact that the two Hilbert spaces are separated. So I'm taking two systems, and each system has a Hilbert space. The combined Hilbert space is just a tensor product. So this relation holds. Are you happy with this? I don't know if you realized yesterday that we needed to use this, but this is trivial. I mean, it's just linear algebra when you assume that the two systems have separate Hilbert spaces. So I have a system. I let it interact with an environment via a unitary interaction according to the second postulate. I assume that the environment, not I assume, I write the initial state of the environment in a spectral decomposition, whatever I like. So I have this expression here. I do all my calculation and I end up with this expression where I like the fact that I can write this expression as something applied to the initial state of my system. As I noticed yesterday, that is not trivial. Be careful. I mean, that is not at all trivial. For instance, if you had that term delta, you couldn't write it like this. There are two non-trivial things in this. One is that neither these nor these operators here do not depend on rho gamma. If they depended on rho gamma, you couldn't write this. Okay? And this is not an operator acting on your initial state. And that is the reason why it's called quantum operation. This is not like taking an operator and applying it to your state. It's just transforming your state with a quantum operation. What is a quantum operation? It's something that works like this. Sometimes it's called a super operator. It's an action on an operator, which is not just multiplying for another operator. Okay? Please. Most of the time it is not. But the reason why it is not invertible, I mean, it really depends on how you define invertibility in this sense, because these objects, the map, and that's the reason. Okay, so let me just speak about the dependencies of this map. This map depends on T. Okay, so with respect to T, it may be invertible, but it also depends on this. So the map depends on the initial state of the environment. So when you write it like this, you've already traced out the state of the environment at the final time. So it is not invertible by definition, because you've lost the initial time of the environment. Do you understand what I mean?
No, I think that the state of the environment is always that you can always treat this video.
Pardon?
You can always go back to a Boltzmann distribution for the environment.
No. There's no thermal bath here. No Boltzmann distribution. No. I mean, in this approach, environment doesn't mean thermal bath. Environment can also be another qubit. Most of the time it's actually your other qubit when you have a C0. But in general, it's definitely not a thermal bath, because you wouldn't be able to write this with a thermal bath. You can't have a unitary describing the interaction between your system and thermal bath. The scheme with the thermal bath, completely different. In the thermal bath, the Boltzmann distribution is not that of the thermal bath, it's that of your principal system. So what I write here has nothing to do with the thermal bath. Do you understand?
Well, in partial phrase, just environment, so throwing away the system is thermal. It is a Boltzmann distribution.
No.
If it were, under conditions of thermalization and so on.
Exactly.
In this case,
Yes, but what it's written here, this is the state of the thermal bath, is not the state of your system in the presence of a thermal bath at a certain temperature. Okay? So you never have this with a thermal bath, because your thermal bath is classical. The system is quantum, but the thermal bath is simply identified by one classical parameter, which is the temperature. Here you have a quantum environment. Is this clear? I'm sorry I didn't enter this aspect, but this is really relevant. I mean, in this approach, the environment is not a thermal bath because it's quantum. It's a quantum environment. It has a Hilbert space associated to it. And the thermal bath has no Hilbert space whatsoever. Okay? When you study a quantum system in a thermal bath, the system is quantum, but the thermal bath is not. It's just as if you were studying a system in an external magnetic field. It's the same scheme. The magnetic field is something which represents your environment at a classical level via a continuum parameter, which is the field. Thermal bath is the same. It represents your environment via a classical parameter, which is the temperature. I mean, we can speak about this. So the state of the environment here is a real state. It's not the thermal state, because the thermal state is not that of the thermal bath. The thermal state is that of the principal system in thermodynamics. Okay? Okay. Now, one thing that you at this point do, you try to simplify your life and reduce the number of labels. So first of all, you take, for simplicity, so we also do it, and this is also consistent with what we were saying now. You take that the environment at the beginning of your process was not in a density operator, but in a projector. Typically, they write okay, so this is, for instance, a typical situation when your environment is the measurement apparatus. Okay? These processes are, this kind of description is perfect for describing measurements. So if the environment is your measurement apparatus, the first thing that you have to do before starting your measurement is to prepare the apparatus in a sort of dumb state. Okay? Is a state where the apparatus is still and waiting for the measurement to occur. So this is something you can do. You just prepare your environment in a state. In this way, you can lose one label here, and you can simply write this, which is what you usually find in books. Obviously, the dependence on psi of the initial state of the environment is still there, but it's lost. And then you also forget about time, and you write this. Okay, so this is the typical expression you find when describing quantum processes via quantum operation. Okay, so the final state of your system has this form. What are these operators? D, it depends. If you want, you can have an explicit form via this expression. In this case, this P disappear because I've set this equal to, so you can put this one, and this is psi is 0. So this is a quantum operation. Psi runs from 1 up to the dimension of the Hilbert space of your environment. So you have as many operators as is the dimension of the environment. Because of the unitarity of the dynamics that you've used in order to construct everything, this condition holds. Again, what is called the unitary freedom. So this follows from the unitarity of this. But if you want to forget about the origin of this structure as from the unitary dynamics, you can also demonstrate that this must hold in order for this to be a quantum process, meaning that you need to guarantee that this is trace preserving. The final state of your system must be equal to 1. And these bring us to the axiomatic approach to this problem, which is forget about everything I've said so far, okay? You've seen how you construct it. Now you forget about it. I know you are hating me, but... And just take this approach. You have a map that goes from an initial state to a final state. You don't even need to have the Hilbert space, which are the same. You can also check the Hilbert space, but that is... And then you say that this is a UDM, so universal dynamical map, which is the same as saying that is a quantum operation. If and only if E is linear, E is trace preserving, and finally, E is completely positive. These three properties define what is called CPTP, completely positive trace preserving map. So, universal dynamical map, quantum operations, CPTP are all the same thing. Completely positive mean the definition of complete positivity is something that may be discussed tomorrow in the discussion. It essentially means that the map must guarantee that even if your state, initial state, is entangled with something else, the map still will be positive, not only for your state, but also for the state of the system with which you're entangled. We can discuss about it on Thursday, because this would detour again the lesson quite a lot. Just to tell you that complete positivity is a very tricky property and very much discussed. There are communities saying that that is not actually necessary. It's enough to require for positivity, but most of the people believe that complete positivity is also necessary. I promise this is the last name I'm going to use. That is not my fault. I mean, it's the literature. That's why I said that you needed a compass. So how do you put all this description together? UDM, CPTP, and quantum operation. In particular, how do you demonstrate that UDM and CPTP are the same thing? You use this theorem, Stein-Spring theorem. Its formulation, as found in mathematical books, is much more general. So the formulation I'm going to give is the one specifically tailored for these kind of problems. And it also goes under the name the church. Don't ask me why. I have to write it because you find it named like this, of the large Hilbert space. What it says take a CPT map, okay, that goes from operators in a certain Hilbert space into another. For simplicity, I here consider only the case when the Hilbert space is the same. It can be easily generalized. The theorem says that it always exists a second Hilbert space, let me call it H2, and a unitary acting on so it always exists H2 and a unitary and a state in H2 such that Okay, that's the only. Okay, and what is more important, it says that the dimension of the Hilbert space H2 is less or equal the squared of the dimension of H. This is a crucial point. So this point is very relevant because it is essentially the way you put together the different introduction of quantum operations. So you put together the construction via the unitary, which means via this idea of a dynamical evolution, with the construction, the axiomatic construction, and the final expression, which is the one written here. But what it says here is actually that even if your environment is extremely complicated, even if the dimension of the Hilbert space of your environment is terrible, is infinite, it's huge, yet, in order to describe its effect on your system, you can reduce it to something which is just, whose dimension is just twice the one of your principal system. Which is quite trivial if you think about it. If you look back at this expression here, you could have already noticed that, because if you have a Hilbert space, you can, of a certain dimension, the dimension of the Hilbert space of the operators acting on it is just the squared of its dimension. So clearly, these are too many. If you let psi go from 1 to the dimension of the environment, say that the environment has dimension 1 billion, and your principal system is a qubit. This doesn't make any sense, because a qubit, in order to describe the change of a qubit, you can only have 4 operators, linearly independent, because the dimension of the operators acting on a qubit, the dimension of the Hilbert space of the operators acting on it is 4. So that's too many. And this is what is written here. So putting everything together, what I've tried to tell you in this 1.5 lesson was, you have extremely complicated problems where you have environments that are, for instance, spin chains, as we will see, or they are a lattice of ion traps. And you let them interact with simple systems like qubit, whether they be spins or spin 1/2 or 2-level atomic systems. And the idea here is that the environment is not something that you want to forget about. It's not something that is disturbing your system. It's actually the thing that you use in order to control your system. Is the system used in order to apply to your qubit those actions that are necessary in order to implement logical gates. So the environment is not something that out there and simply modify the state of my system in a way that I cannot control. In this scheme, the environment is what you use in order to control or measure your delicate quantum system. And this result tells you that, first of all, you can simply devise, for instance, if you are working with a qubit, for a maximum of 4 operators. Those operators, put into this expression, will perfectly define the process you want to describe. Then, if you want to find what kind of interaction you have to engineer, you have to design in order to implement that logical transformation, that process, then you go back here or even to the lesson we've had yesterday. So you have to get back and write down what unitary will actually implement that logical process. Please.
Yeah, so how can we appreciate the 4 in this case? So what's the physical intuition like that would create the 2 squares effectively for the qubit? So where would the other how would it be the environment of a billion as being incorporated to just another 2 on the dimension? So can you give us like a very intuitive picture? Not on the on the there. So
I don't know what in this case an intuitive picture might be. I mean, you're okay with the fact that if you have a qubit, you don't have so many possibilities to transform it. Okay, so you can only act on it in a limited number of ways. So the environment has, uses a lot of its degrees of freedom in order to organize itself in such a way that the part of the environment that it's actually in contact with the qubit acts on the qubit in that proper way. So the physical intuition can change a lot now, depending on the specific physical scheme you are thinking about. For instance, one that we will see tomorrow explicitly is the following. You have your qubit here, and then you have a spin chain with a certain Hamiltonian, and you have nearest neighbor interaction, okay? And then you have a switch here and a switch here. And what kind of game you want to play. This is your initial state. This is your environment, and this is your final state. So even if the system is different, you don't care because it's perfectly okay with this kind of description. So this is your row out. And you want to see whether this chain works properly in order to transfer a state from here to there, or in order to change it. So here it's clear what happens. I mean, the reduction, where does it come from? Because this many-body system has nearest neighbor interaction in here, and all this game here doesn't, the only reason why it is necessary is that it tailors, it designs this last interaction, which is the only one relevant.
it's local entanglement.
Exactly.
Okay.
Exactly. So this is, for instance, one case. Another completely different case is that of the spin ring, where you have one qubit in the middle, or a couple of qubits in the middle, here, and then you have a lot of other objects, call them spins, so usually they are spin. So these are interacting among themselves. And each of them is also interacting with both of the qubits. So here again, you have another situation. But again, what you see is that all these interactions here are on themselves tailored by the interactions between the spins on the ring. And then they act effectively on these 2 qubits in the middle as if they were just one object.
So this theorem that we will say implies some form of reduction of the environment
Yeah.
on the level of the graduate.
Yeah. Yeah. And you can always use it. Notice that the Stein-Spring theorem, when used for describing a measurement, is the Naimark theorem. So remember that a measurement is nothing but a quantum operation, and these 2 theorems are the same, Naimark and Stein-Spring, with Stein-Spring being the more general one. Okay, so this construction now allows us to model completely different environmental systems in a very schematic way, and the other way around. Today we see it in one way, and tomorrow we will see it in the other, on Friday. What does it mean? It means I don't know how the environment, what the environment is. I don't know the details of its interaction with my system, but I can describe what effect it has on my qubit. And that is the only thing that really interests me and that I really want to study in order to make my device work. So this is what I actually said that this was the last name, but that is not true. There's still one name I have to give you. I'm sorry, it's not my fault. So let me end the lesson with a few examples, which are also essential references for quantum processes. So again, your principal system is a qubit. Now we use the computational basis. The most general form of the density operator is, let me write it like this. Which means essentially that so based on the Stein-Spring theorem, I can write rho out of whatever quantum process in this way. As I said, I promised that was the last name, but that is not true. When you use the Stein-Spring theorem and you reduce the number of operators actually to this one, these operators are called Krauss operators. Now, studying the possibility of transforming an initial state of your qubit into another one goes under the name of studying quantum channels. So what is a quantum channel? Well, it's a quantum process for a qubit. So you have one initial state of your qubit and you transform it into something else. One of the most important processes in this framework is what is called phase damping or decoherence. With respect to the computational basis. If you want to have decoherence with respect to another basis, you have to work in another basis. Yeah, I mean, if you come from the construction we've seen before with the D stands for dynamical, they are a number from 1 to the dimension of the Hilbert space of the environment. If you use the Stein-Spring theorem, so to reduce them just to at maximum of the square of the dimension of that, you call them Krauss operator.
It doesn't have any relation with the qubit, right? We can, rho doesn't have to be rho qubit. Oh yes.
I don't know. I've never seen Krauss operator for a couple of qubits, for instance, but you can also do it. So I have no idea. I mean, I don't know if the name by itself referred to qubits or not. I can't say it. What I know is that the number of Krauss operator is, by definition, less or equal to the square of the dimension of the principal Hilbert, of the Hilbert space of the principal system. Remember, by the way, that it always holds the unitary freedom. Okay, so these operators are not univocally defined, so you can find a lot of combination of operators that still works. So, what are the Krauss operator for this process? Well, okay, so first of all, let me explain what is the process. So you start from the density operator I've written before. And you move into something where the diagonal terms stay fixed and the off-diagonal terms are reduced by yes. Okay. So the off-diagonal term in density operator are called in different ways depending on the literature. Sometimes they are called coherence, sometimes they are simply called off-diagonal and so on. So phase damping simply means that the off-diagonal terms of your density operator reduces. Now this lambda is a parameter and it's, you know, it can depend on whatever. And it can vary with time or not, it doesn't matter. The Krauss operator for this process are only two, and this is their form. So if you put these operators in this expression, you see that the result is exactly that of describing this quantum process. Please.
So in the extreme case that lambda equals 1 is a sigma plus and sigma minus, and in effect the outcome is a totally maximal mixed state. Mm-hmm. Is this the...
Well, it's not the maximal mixed because this maximal mixed would be if this were equal.
Okay, sure. It will have coherence. Okay, sure. But a totally complete state.
Yeah.
But is this the allusion to the physical picture you want to make?
Yeah.
Do you want to take lambda to 1 eventually?
No. You can have a lot of different situations. Depending on the physical process that originates this decoherence. For instance, and that is exactly the core of what I'm trying to tell. So this is a very general process. There are just two operators, but this process can originate from completely different interactions and physical phenomena. Krauss operators, quantum operations, model completely different environment. So first example, if you take that your qubit and you take your environment as an electromagnetic field, or if you prefer, a single mode bosonic system, and you take your qubit described by sigma z. This is a typical Hamiltonian you use to describe a two-level system in the presence of a bosonic system. And is written like this. So essentially you're studying a two-level system in the presence of a single mode bosonic system. The Hamiltonian is this one. These acts on your principal system, on your qubit, and these are the operators acting and describing the field. So this is the interaction picture, the interaction between the two systems. Usually you also add a free term like, but it is not necessary to add it now. So if you go through the construction we've seen yesterday with the unitary, where the unitary is just a propagator related to this Hamiltonian, and you make all your calculation, you end up with this lambda being it's not difficult. You can make it as an exercise. It's actually, you can actually find it in a lot of books. Okay? Which is a very typical situation. You have coherences that go up and down. You know, they appear and they disappear, they appear and they disappear. Okay? Here you have a frequency. Clearly, if you also add the free term, then you have an interplay between the coupling and the free frequency. You can have exactly the same Krauss operator and the same phenomena in a completely different setting, what is called the random phase kick. So essentially, you have a system. You have still your system, which is your qubit, which is in an initial state. And what you do, you randomly flip 0 with 1, exchange 0 with 1. Okay? Randomly with a distribution in time, which is a Gaussian with a certain standard deviation. Okay?
So here, the P operator stands for the environment.
Yes.
The design environment. Okay.
Yeah.
That's a very interesting way to approach it, because usually one would solve the James Cummings and then get the Rabi, but okay, this is a very interesting alternative.
Yeah, I mean, that is the... Okay. So, as I said, completely different situation, random kick, Gaussian distribution of the kicks, and then you have, again, the same kind of process, but now lambda is equal, actually 1 minus lambda is equal to E minus gamma, where gamma is the variance of the Gaussian distribution of your random kick. And I could go on with other examples. I mean, the message is you can have exactly the same state transformation, the same quantum process, with completely different environment, with completely different time dependence, depending on the microscopic process originating the change in the state, and yet the description in terms of quantum operation is exactly the same. Please. Pardon? Yes. Yeah. Yeah, as I said, I mean, the Hilbert space of the bosonic mode has dimension equal to infinity. Who cares? The Krauss operators are 2. That's it. Okay. Now, these things might sound, now that I've told you, sounds slightly trivial, but actually, in order to get to the formal construction, requires a lot of mathematics and a lot of theorems. Once you have them, though, you use them, and they are extremely powerful. So these are definitely the instrument that you use when you want to study how a quantum system changes its state due to some process. Okay? I think. Questions? In the box, the questions that I find in the box today will be answered tomorrow in the discussion. The author of that one, please, either you don't care or allow me to use it in my website. If I don't find anything, I assume that you allow me to use it. Okay.